Okay, so get this. We're about to go deep on how Rust actually stores data in the computer's memory.
Yeah, it's way cooler than it sounds.
It really is. And trust me, knowing this stuff can turn you into a total Rust ninja.
Totally. It's like learning the secret handshake for writing crazy efficient and super reliable code, even if you're building like apps that seem miles away from low-level stuff.
Right. Our source material today is like a crash course in all things Rust memory.
And it all starts with this wild concept of virtual memory.
Okay, so virtual memory is like, imagine your program needs like a workspace, right?
Desk.
Exactly. A desk. Well, Rust basically gives your program a desk the size of a small planet.
It's huge E,
Seriously huge, like terabytes and terabytes of space.
which would be insane if it were all real physical RAM.
Right, that'd be nuts.
So instead, the operating system, it acts like this super organized, like, librarian, I guess. It keeps track of which parts of your program's giant desk are actually being
Oh,
used.
that's interesting.
And it only pulls those specific files, the memory chunks you actually need, into real RAM.
Okay, so it's like those maps where you only see the details for the area you're zoomed in on.
Yeah.
The rest is just like potential space until you need it.
Precisely. That's virtual memory in a nutshell.
Super clever.
Ah.
So our program thinks it has this ridiculous amount of space.
And the operating system makes sure it actually gets what it needs without, crashing your computer.
It's a win-win. So smart. Okay, but let's zoom in a bit from that planetary disk view to something a bit more, well, manageable.
Right, because within this virtual memory space, things get organized into two main zones, the stack and the heap.
The battlegrounds of memory allocation.
Okay, so picture this. You've got a short order cook, super efficient, working with a perfectly stacked pile of plates. That's your stack.
Okay, I'm with you.
And each time that cook, or in our case, our program needs to whip up a new dish, they grab a plate off the top. That plate is like a stack frame holding all the ingredients for that specific dish.
So each function call is like adding a fresh plate to the stack, loaded up with its own ingredients.
You got it. And just like our efficient cook, when a function finishes doing its thing, it's time to clear the plate. Boom, off the stack it goes. No mess, super organized.
Fast too, right?
Blazing fast. But here's the thing about the stack. It's got limited space.
Right. You can't fit all your leftovers on that stack of plates. You need, like, Tupperware for that.
Exactly. And that's where the heap comes in. Our more flexible storage solution.
The heap is more like that one room you have where you just put stuff, that glorious catch-all.
Not as organized, but it's perfect for larger items that need to stick around for a while.
Though finding things in there might be a bit slower.
That's the trade-off. The heap gives you flexibility, but accessing data on the heap can be a tad slower than that super fast stack.
Right. Just like finding that one thing you need in your catch-all room.
Yeah.
Sometimes it takes a bit of digging, but hey, sometimes you just need that extra space.
Absolutely. And knowing when to use which the stack versus the heap, that's key for writing efficient code. It's all about using the right tool for the job.
Picking the right storage locker for your data. Okay, I'm loving these analogies. So we've got our virtual memory desk. We've divided into our neat stack of plates and our more flexible heap. But how do specific Rust data types actually fit into this picture?
Yeah, let's get down to the nitty-gritty.
Let's start simple. Integers. Those got to be pretty straightforward, right?
They are integers. Think of them like those little sticky notes you can put anywhere, small, compact, easy to manage. Perfect for our stack of plates.
Integers are trusty sticky notes,
Yeah.
right next to the function's other ingredients.
Exactly. Now, what about tuples?
Tuples. I always think of those like those little suitcases, like different compartments for different data types, all packed up neatly.
And just like a well-packed suitcase, tuples belong on the stack too. They've got a predictable size, so they fit right in.
Okay, so integers and tuples are happily hanging out on our stack of plates. But what about arrays and vectors? They both store sequences of data, but I have a feeling they don't always play so nicely with our limited stack space.
You're right about that. Arrays, they're a bit more like those spice racks. Each spice has its own little designated spot.
Perfectly organized.
Exactly. And that's why they work well on the stack. We know exactly how much space they'll take up, nice and predictable.
Like those little integer sticky notes and our compact tuple suitcases. Okay, but vectors. They're a bit more like those magical suitcases, the ones that can somehow fit an entire wardrobe.
Ah, yes. The Mary Poppins bags of the Rust world.
You start packing, thinking there's no way it's all going to fit, and then bam, there's always room for more. How does Rust even fit that kind of magic onto our neat little stack?
It's all about clever tricks, really. You see, the actual contents of a vector, all those clothes you're packing, they live on the heap.
Ah, the heap, of course. We
Yeah.
need that extra space.
Exactly. More breathing room over there. But here's the cool part. On the stack, we keep a little treasure map, a vector header.
Ooh, a treasure map. I like where this is going.
This header, it tells us everything we need to know about that vector.
So it's like a signpost, pointing to where all the goodies are actually stored on the heap.
Precisely. It stores a pointer to the heap location,
Mhm.
the number of items currently in the vector, its length, and get this, how much extra space it has reserved its capacity.
It's like knowing how much more you can cram into that suitcase before needing a bigger one.
Exactly. So even though vectors can grow and shrink dynamically, Rust keeps things organized and efficient.
I'm loving this system.
So smart.
Okay, let's talk about strings. Strings. They're kind of like the words that make up our code story. And Rust has, like, this whole other way of storing them.
Oh, yeah. Strings are fascinating, especially string literals. You know, the strings you actually type directly into your code?
Right, like the name of a variable or something.
Exactly. Those get special treatment in Rust.
Our source material mentioned that something about storing them directly in the compiled code itself. What does that even mean?
Okay, so imagine you have a bookshelf, but instead of books, it's filled with your favorite quotes, the ones you use all the time.
Okay, I can picture it.
That's essentially what Rust does with these string literals, stores them right there in the compiled code, so they're super fast to access.
It's like having those quotes instantly pop into your brain. You don't even have to think about it.
Exactly. No need to mess around with the stack or the heap.
Genius. But wait, what about variables that hold these string literals? They have to go somewhere, right?
Absolutely. The variable itself, it lives on the stack.
Yep.
But instead of storing the entire string, it acts like a bookmark pointing to that specific quote on our compiled code bookshelf.
So the variable is like a little note saying, hey, go check out this awesome quote. It's on the third shelf, second from the left.
Exactly. We call this a string slice, a lightweight reference to the actual string data. Efficient and elegant.
Very cool.
Yeah.
But what about those strings that, like, change? Like, say, something a user types into a program.
Those are a different story. We don't know how long those strings will be in advance, so they need the flexibility of our heap.
Just like those magical vectors.
Exactly. So the string content itself goes on the heap, and then on the stack, we keep a little header that points to the heap location and tracks its length and capacity.
Same strategy, different data type. It's like Rust has this whole organizational system figured out.
It's all about efficiency and safety. Now, ready to level up to some even more interesting data structures.
Oh, I think I know where this is going. Our source mentions structs and enums. Those are like the Lego bricks of building custom data structures in Rust.
And just like Legos, the way a struct is laid out in memory depends on how you've assembled it. Let's say we have a struct representing, I don't know, a book with fields for the title and the number of pages.
So it's like having a custom shelf for each book, with compartments for the title and number of pages.
Precisely. And the compiler, it neatly arranges those fields in memory, one after the other. Now, remember how strings can sometimes live on the heap?
Oh yeah, those string slices, or little bookmarks to the, quote, bookshelf.
Exactly. If a struct contains a string, it's like having a little treasure chest on that bookshelf instead of the actual text.
A treasure chest. Okay, I'm really liking where this is going.
And inside that treasure chest is a pointer telling us where to find the full string on the heap.
So even though part of the data might be stored elsewhere, the struct itself stays nice and organized on the stack. I love how everything has its place in this system.
It's all carefully orchestrated. Now, enums, they're a bit trickier. It's like having those mystery boxes. You know one prize is inside, but you don't know which one until you open it.
Okay, yeah. So how does Rust deal with that? How do we know where to find the right prize in memory? Okay, mystery boxes, enums, lay it on me.
All right, so remember, an enum, it can hold like different types of data depending on the variant, right?
Yeah, like it could be an integer or it could be a string, all living in the same enum house.
Exactly. So the compiler, it has to be ready for anything. It needs enough space to store the largest possible variant.
Even if, like, right now, my enum is just holding a teeny tiny number, the memory space is still, like, reserved for something much bigger.
That's right. It's like having a set of gift boxes, but you have to pick the box size before you know what the gift is going to be.
Just in case you need to fit, like, a giant stuffed animal in there.
Exactly. But here's the really clever part to keep track of what's actually inside. Enums use this extra bit of memory called a tag.
A tag. Ooh, okay.
It's like labeling that gift box so you don't have to unwrap the whole thing just to see what's in it.
Makes sense. So we're not constantly guessing, is this the integer box? Is this the string box?
Yeah, exactly. The tag tells Rust, hey, this enum, it's currently storing this variant, so it knows how to handle the data. Pretty slick.
Super slick. Okay, enums. I'm impressed. We've covered so much ground here, from virtual memory all the way down to these clever little enum tags. But our deep dive isn't over. Our source material also talks about these things called smart pointers. And to be honest, they sound a bit intimidating. Do I need like a computer science degree to understand these things?
Not at all. Smart pointers, they're like Rust's built-in memory management buddies. They help us keep our code clean and like prevent those nasty memory leaks that can crash everything.
Okay, so they're actually on our side. That's good to know. Our source focused on three main types: boxes, RCs, and ARCs. Let's start with boxes. They seem like the, I don't know, the friendliest of the bunch.
They are. Boxes are like our go-to for simple heap allocation. Remember the heap, that room where we store things long-term?
Oh yeah, our heap catch-all.
A box is like renting a dedicated storage unit in that room.
So we've got the heap room, and then our box is like a clearly labeled container within that room.
Precisely. The box itself actually lives on the stack. It's just a little pointer to that storage unit over on the heap. And the beauty is, when you're done with that storage unit, when the box goes out of scope, it handles all the cleanup automatically.
No need to, like, call the cleaning crew. It just, poof, takes care of itself.
Exactly. The box handles it for you. Now, sometimes you need to share that storage unit with others, and that's where RCs come in reference-counted pointers.
Ah, shared access. Like a Google Doc for data.
Perfect analogy. But with RCs, we need to make sure no one accidentally deletes the doc while someone else is still using it.
Right, memory safety first.
That's what RCs are good at. They keep track of how many keys or references exist to that shared data on the heap. Each time you clone an RC, it's like making a copy of the key.
So if I've got three variables all pointing to the same data on the heap, all using RCs, there are three keys in circulation.
You got it. And here's the magic. Only when the last key is returned, the last RC goes out of scope, is that data actually freed from the heap.
So it's like a memory safety pact, no deleting until everyone agrees they're done.
Exactly. And finally, we've got ARCs, our thread-safe superheroes. They're like RCs, but with like an extra layer of protection for when you're dealing with multiple threads.
Ooh, threads. Always makes me think of those movies with, like, multiple timelines happening at once.
Haha, kind of. So you've got these threads, these independent workers in your program, all trying to access the same data. ARCs make sure that doesn't cause a chaotic mess.
So they're like the traffic directors of memory access, making sure everything stays organized, even with all that parallel action going on.
Precisely. ARCs use these things called atomic operations super fast, synchronize actions to make sure those reference counts are always accurate, even with multiple threads in the mix.
ARCs, the ultimate multitaskers of the memory world. I am loving this.
They're pretty impressive, right? And the best part is, Rust handles most of the complexity behind the scenes, so we, as developers, can focus on writing awesome code without having to micromanage every little memory detail.
It's like having a whole team of memory ninjas working behind the scenes, making sure everything runs smoothly. This has been incredible. I feel like we've really journeyed through like the entire landscape of Rust memory management, from the big picture view of virtual memory all the way down to these like intricate details of smart pointers.
I don't know about you, but I feel way more confident in my Rust skills now.
Absolutely. It's like we've unlocked the secret language of how Rust thinks about memory,
Yeah,
and that is a seriously powerful tool to have.
it really is. And to all our listeners out there, if this deep dive has sparked your curiosity, if you're ready to level up your Rust game, go forth and explore.
The world of memory management might seem a bit intimidating at first, but honestly, with Rust as your guide, it's a fascinating and honestly surprisingly delightful journey.